what we're going to do now is introduce you to a technique that can be used to compare two population proportions. The technique is called a randomization technique. And we're going to go through a scenario to help you understand this. The methods that we're going to learn here apply to when you have two levels of a treatment or two distinct groups. So this applies to independent sampling, where you're comparing two groups, or it applies to a completely randomized design where you have two levels of a treatment, say a control group and an experimental group. The other thing to understand is that these methods only apply when the response variable is qualitative with two possible outcomes, which lends itself to being analyzed using proportions. So to help understand the logic behind this randomization method, let's look at a scenario. A flipped classroom is one in which students learn material through video and other activities at home, while class time is dedicated to group learning and peer-to-peer instruction. Professor Line wanted to know if introductory statistics students taught using a flipped classroom resulted in a higher proportion of students passing over her traditional lecture-based model of teaching. So one semester she taught one section of intro stats using the flipped model and one section using a traditional lecture model. At the end of this semester, she recorded whether a student passed or did not pass the class. And then finally, any student who withdrew was recorded as a student who did not pass. Results are shown in the table below. And so you can see here that in the flipped classroom, 25 of the students passed and 7 did not pass. In the traditional classroom, 21 students passed and 11 did not pass. And so the question we ask is, does this sample evidence suggest the flipped course is superior to the traditional course as measured by pass rates? So again, we're comparing two groups, flipped and traditional, and the response variable is whether the student passed or not. So that's a qualitative variable with two possible outcomes. Again, we have two courses being compared. The experimental units in this study are the 64 students, the 32 in the flipped and the 32 in the traditional. Now, the assumption that we would make going into the start of the semester is that these students are the same in terms of academic ability. In other words, the students that are in the flipped course have the same likelihood of passing as the students in the traditional course. And so that the only variable that we're manipulating here to see whether the course is effective is the delivery mechanism, flipped versus traditional. It is worth pointing out that there is a potential confounding variable in here, and that's time of class. You can't do anything about that. Okay, so even if one course is offered at Monday, Wednesday, Friday at 8 a.m. and the other at 9 a.m., class time could be a variable that affects the response variable. We just have to acknowledge that there's nothing that we can do about it. So if we look at the sample data, the proportion of students in the flipped course who passed is 25 out of 32, or 0.781. And the proportion of students in the traditional course who passed is 21 out of 32, or 0.656. And so the difference in sample proportions is 0.781 minus 0.656, or a difference of 0.125. And so we have a question now, some questions that we want to ask. First, is that difference in sample proportions statistically significant, suggesting that the flipped course has a higher pass rates than the traditional course? Or Is it possible that this difference is simply due to random chance and there is no difference in the pass rates of the two courses? In other words, is it possible the 46 students who passed, that's right here, these 46 students passed, is it possible those 46 students would have passed regardless of whether they went into the flipped or the traditional classroom? And we just happen to get a higher proportion of these passing students enroll in our flipped classroom. And so those two questions lead to two possibilities. First, the flipped classroom is not more effective, and that higher pass rate was simply due to random chance. That is, the proportion of students who passed the flipped is equal to the proportion who would pass the traditional. The second possibility, the flipped course is more effective, and this is what is explaining that difference in pass rates, the difference of 0.781 versus 0.656. That difference is a result of the delivery mechanism. Flipped is a better model than traditional. And so we can state these two possibilities symbolically using the language of hypothesis testing. The first statement, that the flipped course is not more effective than the traditional course, would state that the proportion who would in general pass the flipped equals the proportion in general who would pass the traditional. And then the second statement right here is symbolically written this way. The proportion who passed the flipped is greater than the proportion who passed the traditional. So in plain old English, the null hypothesis is stating there is no difference in the overall pass rates between flipping and traditional. The second statement, the alternative statement, is saying the proportion of students who pass using the flipped model is going to be greater than the proportion passing in the traditional model. And we can also write these statements as a difference. Proportion of flipped minus proportion traditional is 0, is the null. And the alternative is that the proportion flipped minus the proportion in the traditional is greater than 0. Remember, whenever we do hypothesis testing, we always build our model assuming the statement in the null is true. The statement in the null is a statement of no effect, no difference, meaning the pass rates in the flipped is going to be the same as the pass rate in the traditional, because there's no difference in pass rates regardless of the way you teach the course. To build the null model, we're going to use an urn. The urn is going to have green balls and red balls. We're going to have 46 green balls, and those 46 green balls are going to represent the 46 students who passed right here. And then we're going to have 18 red balls. The red balls are going to represent those students who did not pass. We're going to put those balls in an urn, mix the urn up, and then randomly select 32 balls from the urn. Those 32 balls are going to be the 32 students who enrolled in the flipped course. So if you think about this for a second, the 46 green balls are 46 students who would pass. They would pass whether they enrolled in traditional or flipped, because the color of the ball doesn't change. The 18 red balls are students that are not going to pass regardless of whether they enroll in the traditional or the flipped. So again, that's the statement in the null. What course you enroll in does not matter. You're going to pass either way if you're going to pass, and you're going to fail either way if you're going to fail. And so by randomly selecting 32 balls, we're doing this under the assumption the statement in the null is true, because you have the same chance of being enrolled in the flipped as you do in the traditional. So rather than literally doing that with an urn, we can do this using StatCrunch. So we're going to go applets, simulation, urn. 46 green balls. 46 green balls are the 46 passing students, and 18 red balls are the students that do not pass. Okay. So the green, there's going to be 46 of them, and the red, 18 of them. Again, the green balls are students that pass. The red balls are students who do not pass. We're going to draw 32 balls. These are the 32 students who are going to go into our flipped classroom. Okay?
Mm-hmm.
And then here, under number, we're going to say number greater than or equal to 25. Why? Because if you recall way back here, 25 is the observed number of students in the flipped classroom who passed. Okay, so we're ultimately going to want to see how often do I see results as extreme or more extreme than those actually observed. How often do I see 24, 25 or more passing in the flipped course? So we'll just title this flipped versus traditional. And we click compute. So here's what we're going to do with this earn. We're going to pretend that we're teaching the traditional and the flipped classroom over and over and over again. We're going to allow our students to randomly enroll in either the traditional or the flipped classroom. The 32 balls that we randomly select out of this earn are the 32 students who chose to go into the flipped classroom. Okay, so when I click one run, these 32 students enrolled in the flipped classroom. The red balls are the students who did not pass. The green balls are the students who did pass. So I had 22 pass. Okay, remember, the color of the ball was determined before I picked them out of the earn. Meaning, whether the student passed the course or not was determined prior to them enrolling into the class. That's the statement in the null. How I deliver the course does not matter in terms of whether the student's going to pass or not. So I observed 22 passing. Let's teach the course one more time. One run. I teach the course. This time 24 students pass. Now I want to do this many, 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 many times. Using the earn applet, I can just click 1,000 runs. I'll click 1,000 runs, it's a total of 5 times. So we're literally going to be teaching the course 5,002 total times. And you can see out of the 5,002 times that I taught the course, 1,010 of those times I had 25 or more students pass in my flipped classroom. So the proportion of times that happens is 0.2019. This 0.2019 is the p-value for the hypothesis test. Let's think about this. In about 20 of every 100 times I teach this course, I'm going to see 25 or more passing in the flipped classroom, even though the style of the way the course is taught does not matter, does not play a role in pass rates. And so it's very, very easy just due to random chance to get 25 or more passing in the flipped model. And that would mean we're not willing to say, oh, everybody switched to flipped classroom because it's an effective teaching method. Our results are not bearing that out. You could easily get those results due to random chance, because we did get them due to random chance, pulling the balls out of the earn.
So even though it's over, like, I guess the level of significance, if you go like 0.05, are we basing it on that, I should say, like that it it goes over like when you compare the two, the level of significance to like the proportion or p-value, that it is above. So wouldn't that make the flipped course more likely though to be used like significant? Like,
let's think about what this 0.20 is saying right here, okay? This is saying, well, first of all, how did we get to 0.20? We had 46 students passing, 18 did not pass, right? Overall. We randomly selected 32 students and recorded the color of the ball. In other words, recorded whether the student passed or not. And then we said, how often did we get 25 or more passing when we randomly selected 32 balls? Notice that these 46 balls here, these 46 these 46 students were passing whether I randomly picked them or not.
Okay.
And these 18 students down here were not passing whether I randomly picked them or not. So in the context of this problem, when I randomly pick 32 students, these students here are going to pass whether I put them into the flipped classroom or I don't.
Okay, so it's already bound to happen then.
Correct.
Okay.
So that's the statement of no effect. The course delivery mechanism has no effect on whether you pass or not. That's the statement in the null. And that's what we're assuming when we built this urn. And so what we're saying is, assuming the course delivery mechanism does not matter, we would observe 25 or more students passing in a flipped classroom in about 20 of every 100 classes. And so the fact that we observed 25 students passing is not at all unusual. And so you would conclude from this, there is not sufficient evidence to suggest, there is not sufficient evidence to suggest course delivery mechanism or means or whatever affects pass rates. Right? Flipping is not superior to traditional, according to our data. What's nice is we don't have to use an earn applet to estimate the p-value. I mean, the earn applet has a lot of intuitive appeal, if you ask me, because you can see the balls were going to be green and therefore the students were going to pass whether we had them in the class or not. But now what we want to do is look at this from a different point of view using something called a resampling applet. Go ahead and open up some raw data for you. So this data here is the observed results. The first column represents the course that you're in, whether it be the flipped or the traditional. And then the second column, outcome, is whether you pass the class or not. And so we had 25 in the flipped classroom pass, and then the rest did not pass. And then here are the students that passed in my traditional, and these are the students who did not pass. See how I have a total of 64 students, 32 in the traditional, 32 in the flipped. We can use this raw data to build the randomization applet. You select applets, resampling, and it's called randomization test for two proportions. Now we have to select our data. We're going to select the outcome, and then we're going to do where course equals flipped. And we're going to label this the flipped students. And then for sample 2, we're going to select the outcome where course equals traditional. And when you type this out, it's case sensitive. So if there's a capital C in the title, like there is here, you have to use capital C under the where. Flipped is spelled with a capital F, so you have to put a capital F here. It's case sensitive. And then label this traditional.
There's no spaces in between traditional and equal. Anything like that?
No, no spaces.
Okay.
And then a success is passing the class. Okay, so basically what I'm doing here is these 32 students represent sample 1, the flipped students, and then sample 2 are my traditional students. The variable is the outcome. That's why I'm selecting outcome, right? Whether you pass the course or not. You're going to have to use fixed seeds. I'm going to use a dynamic seed. Click compute. And I'll just do this one time so you can see what happens with the applet. Pay very, very close attention to what happens on the applet. We randomly assign the course to the outcome. Did you see how the sample column flipped around? We're randomly assigning the course to the outcome, meaning whether you enroll in a traditional or a flipped classroom is not going to play a role in whether you pass the course or not. That's the statement in the null. And then we're going to see how often do I observe a pass rate difference in pass rates of 0.125 or higher, because that was the sample difference in proportions that we computed. So if I do this over and over and over again, so there we are 5,002 times, you can see we observed a sample difference in proportion of 0.125 or higher about 21% of the time. There's my p-value. So here the p-value is 0.2019. Here the p-value is 0.2073. The p-values differ because of the randomness involved in the assignment, the randomness of the assignment of the course. Okay, they're going to be close, but they're going to be slightly different from each other.
So does this edge the other one out then?
I wouldn't say edge the other one out. Both of them are not giving us evidence to suggest that the course is flipping the classroom is going to result in a higher pass rate, because you're getting a very large p-value, right? You would observe the results that you observed about 21 out of every 100 times you did this. If the statement in the null that the pass rates are the same is true. Okay, so when we did it this time, the p-value is 0.2073. And so we would say if there is no difference in the pass rate of the two courses, in other words, if there's no difference in the pass rates between traditional and flipping, we would expect a sample difference in proportions of 0.125 or higher in about 21 of every 100 repetitions of this study. So the observed results are not unusual under the assumption the pass rates of the two courses are equal. We did not observe unusual results, and therefore there is not sufficient evidence to suggest the pass rate of a flipped class is greater than the pass rate of a traditional class. You know what, before I go further, I think it's worthwhile, suppose instead of, let's go back to my urn. Suppose we had 28 students pass in the flipped classroom instead of 25. If 28 students pass, the likelihood of getting 28 or more passing in your flipped classroom, under the assumption the pass rates in the two courses is the same, is only 0.005. In other words, you would only observe results such as this about 5 of every 1,000 times you did this study, if the pass rates of the two courses were the same. Because observing a result such as this is so unusual, under the assumption the pass rates of the two courses is the same, you would take this as evidence against the statement in the null. And you would take this, therefore, as evidence that, yeah, the pass rates in the flipped classroom are higher than the pass rates in the traditional. Remember, the lower the p-value is, the stronger the evidence against the statement in the null. Our null is that the pass rates of the two courses is the same. And so this low p-value here, only observed 25 times out of 5,002 times we did it, suggests that, hey, this result is very unusual, and therefore I'm going to take that as evidence against the statement in the null and say there is sufficient evidence that the pass rate in the flipped classroom is greater than the pass rate in the traditional. Now, what I want you to notice is look at the shape of the outcomes in this difference of sample proportions. What kind of shape does it have?
Bell shape.
Pretty bell-shaped, which suggests, hey, maybe I could use the normal model to approximate the p-value as opposed to going through this randomization technique. Notice the difference in sample proportions is also centered about 0. That should make sense to you. It's centered about 0 because that's the statement in the null. There is no difference in the proportion of students who pass in flipped versus traditional. But also notice that there's natural variability in the distribution of sample proportions. That natural variability is what we have to account for using the standard error. So here are the steps that you can take to test hypotheses regarding two proportions using random assignment. First, the explanatory variable has to have 2 levels, and the response variable is qualitative with 2 possible outcomes. Either you have a characteristic or you don't. You determine the null and alternative hypotheses, and they can be structured using the typical ways. Equal versus not equal, you're two-tailed, a left-tailed, which means a less than alternative, or right-tailed, which means a greater than or alternative. The null is always a statement of no change, no effect, no difference, and therefore is always a statement of equality. We then build our null model around these hypotheses, assuming the statement in the null is true. We estimate our p-value based on that null model or the outcome of that null model, and then state our conclusion.